do that graphing discovery activity and you like worked on that problem where it asked you like, could you build a snowman? You probably created Limacons. Because what happened when you were trying to build a snowman was you could get a circle below the axis if you used a negative sign. You could get a circle above the axis if you used a positive sign. And then you needed to like get a full three-bodied snowman, you would need a circle like higher up or lower down. So you probably started adding and subtracting numbers like you were trying to do vertical shifting, which is awesome because you know about vertical shifting. But what you find is you don't actually get to vertically shift in a polar coordinate system. Everything has to be connected to the pole. So, no good. You probably saw some strange looking shapes depending on which values you decided to plug in. They might have just looked like flat circles or they had like different loops in them. So that's what the Limason is. Notice that as you wrote down the equations for the Limason, you'll be able to easily tell these from circles and rose curves because plus or minus, right? There's a plus or minus and it's a Limason today. Okay. Now it won't be both at the same time, it'll be one or the other. Okay, so it'll be like a plus b sine theta or a minus b sine theta, but not both. Okay, let's see. Here are some things to note. The sine or the cosine, so whether it's a cosine theta or a sine theta Limason is going to determine symmetry. And this actually is true from yesterday as well. We noted it for each of the circles and for each of the rose curves. If it was a cosine circle, if it was a cosine rose curve, it had horizontal symmetry. The same is true for the Limason. If it has a cosine Limason, it has horizontal symmetry. That means once you graph your Limason, if you like fold your paper at the horizontal axis, the Limason would map onto itself. And then anything in polar graphs that has a sine function in it is going to have vertical symmetry. Okay, so this is really nice to make a connection across all of the polar graphs. It doesn't change for circles, rose curves, or Limason. It remains the same. Okay, the plus or minus. So whether it's a plus b sine theta or a minus b sine theta, it is going to determine, I'm going to describe it as the orientation. Which I also agree we actually already did yesterday. So like I have over here on this sideboard, here's a cosine theta circle with a positive a because it's to the right of the vertical axis. And then here's a cosine theta circle with a negative a because it's on the left side, right? So positive meant right for cosine, negative meant left. And then if it was sine, positive was up and negative was down for the circle. If you want a little bit more about orientation, you could write down the 4 possible equations. A plus b cosine theta, a minus b cosine theta, a plus b sine theta, and a minus b sine theta, and just kind of like jot down their orientations next to them. Of course, the cosines are going to be right and left. If it's plus, it's going to be to the right. If it's negative, it's going to be to the left. And then if it's sine, remember it has vertical symmetry. Sine is a vertical movement, so that's going to be up and down. If it's positive, it's up. If it's negative, it's down. When we get to the graphs, what this should coincide with is this is where the majority of your graph shows up. The majority of the Limason is to the right. Some of it will be to the left, but the majority of the Limason is on the right if it's an a plus b cosine theta. Okay, we've got a max R value. defined by absolute value of A plus absolute value of B. So now that we have the two, the A and the B working together, the maximum value that we can get outputted to us is the absolute value of A plus the absolute value of B. So ignore their signs. And then we'll also look at the ratio for the absolute value of A over B, and this is going to determine the shape of your limacon, or you could also think about it like the type of limacon. So within the limacon, there are 4 different shapes that can occur. Okay, so these 4 graphs appear on page 751 of your textbook. And you might want to jot down that page number like in the margins of your paper, of your notebook, in case you ever want to see the graphs in the textbook again. They have a lot more other information with them in the textbook, but I only took the pictures. Okay. I would encourage you right now to attempt to sketch them in your notebooks so that we can name them and talk about what ratio produces this type of limacon. To kind of help you out with this one, note that this like turning point right here, this is going to be called a loop. This loop will intersect at the pole. Okay, so that's where it will cross over itself. And this one is actually touching the pole right there. So there is a point at the pole on those two. Oh, the second graph. Just like where it comes in, touches the pole, and it bounces off. There isn't a loop in the second one. I'm going to call it something that sounds like heart. So it's like if you drew a heart. Comes in, touches it, and moves out. Oh my gosh, these are beautiful limacons as I walk around the room.
Kidney beans.
Kidney beans. Lima beans. Right? Is that what those are called? Lima beans? It's been so long. Okay, I'm going to name these shapes. Okay. This first one we're going to call limacon with a loop. Very creative. It has a loop in it. It's the only one. The second one has a fancy name. It's called a cardioid. And what word do you see in there? Cardio, which means heart. So I think about it like when you draw a heart, right? The top of the heart, you like come into the middle and then you bounce back out. That's what's happening right there at the pole. Okay, this is called a dimple, or with a dimple. So, think about like when you smile, if you have a dimple, okay, it indents in your cheek, right? I always wished I had dimples. This one is called convex. It's the only one that's convex. Convex, if you remember back to geometry, convex means that you pick any 2 points on the perimeter of the shape and draw a line connecting those 2 points. That line has to pass through the middle of the shape. It's never on the outside of the shape. All of these other ones, like the limacon with a dimple, I could connect these 2 points and my line would be outside of my shape. So those are non-convex because that can happen on all of them. Okay. But this one is convex, so think about it like almost like a circle, but it's kind of flat on one side. And how flat it is depends on the ratio of A to B. Okay, so when is the limacon each of these shapes? It depends, remember, on the ratio of absolute value of A over B. So if the absolute value of A over B is less than 1, you're going to get a loop. because we're talking absolute value, that also means it has to be greater than 0. We don't have to worry about negative ratios. If the absolute value of A over B equals 1, oops, not 4, equals 1, it is a cardioid. So it'll come in, touch the pole, move out. If the absolute value of A over B is greater than 1, but at the same time less than 2, you get a dimple. And then anything greater than or equal to 2 is convex. So it's kind of like you start with a loop and then you move out to just like a heart, and then you move out to just kind of smooth curve inward, and then to convex as the ratio increases. It gets larger. Okay, one last thing before we get into our graphs is we'll get some of the same characteristics as we did yesterday. So there will be the question about the number of zeros that the graph will have. So just by looking at the picture of the Limacon, let's start over here with convex. How many zeros does it have? None. No zeros. It never touches the pole. Some of your Limacon will be on the left. The majority of this Limacon is to the right, so it must be an A plus B cosine theta. But you'll see a little bit on both sides. It's not like all on the right side, like a circle. How many zeros does this have? None. Never touches the pole, so no zeros. For a dimple either. The dimple, the little like indent in, will happen on the other side, but it won't actually ever get to the pole. So if it's a dimple, don't go to the pole. Okay. Cardioid has how many zeros? 1 0. It comes in, touches it, moves back out, so we count that as 1 touch. And then to create a loop, how many times do you have to cross the pole? 2 times. So 2 zeros. One's on the way in and one's on the way out. Okay, let's do some examples. First example, r equals 2 plus 3 cosine theta. Okay, think about tomorrow. You're going to take a quiz. You're going to have to graph all 3, circle, rose curve, Limacon. How can you tell by the equation that this one is a Limacon?
Plus.
It's got a plus or a minus, right? If you got extra numbers in there, it's automatically Limacon for us. So we know it's a Limacon. Just like yesterday when we would say, like for rose curve, we would say rose curve with 3 petals or rose curve with 4 petals. When you name the Limacon, I would say what kind of Limacon it is. So right away, you're going to do the ratio of A to B. What is that? 2 over 3? So that's less than 1, which is Limacon with a loop. Okay, how many? What's the max R value going to be? 5. And the number of zeros, 2, because it has a loop. So we're going to have to cross it twice. If you want, at that point that you know it's a loop, you can put like a little point at the origin because you know it crosses through the pole 2 times. So you can put a point there if you want. Okay, now, after you would tell me it had 2 zeros yesterday, what would you have to do? Actually find the zeros. Notice that that is no longer part of your work. Reason being, this is going to be no calculator, so like, can you make the polar graph without plugging it into your calculators? Okay. And if I did this one to solve, plug 0 in for r, and then solve for theta, I would subtract 2, divide by 3. So that would be negative 2/3 equals cosine theta, without a calculator, can you tell me what that angle is? No, because those are not values from the unit circle. So we're not going to restrict ourselves to values from the unit circle, so we just don't have to find the zeros. It doesn't really matter what angle it happens in all reality here. Like we used it yesterday to like find the middle of the two zeros so we could get the end of our petals or the diameter of a circle. But today, like, you know it passes through the origin at the loop, like at the pole to make the loop. You don't really care what the angle is because you're going zero. So it doesn't really matter. But that leaves us with, like, we need to fill in our significant points. And the Limacons are the more complicated shapes. So we actually would probably benefit from having more points. Think about angles that you could be plugging in for this cosine. You'd have to multiply it by 3 and add it to 2. Wouldn't you like your numbers to work out nice? Integers, no fractions, no radicals. What are good angles for that on the unit circle in terms of sines and cosines? Quadrantal angles, right? If we put in 0, pi over 2, pi, 3 pi over 2, we're going to get out ones, negative ones, and zeros, and that would be great. So let's do that. 0, pi over 2, pi, 3 pi over 2. If you want to put 2 pi in your table, you can, but 2 pi is coterminal with 0, so it's going to be like, okay, we go back to our first point. Okay, to get your values, plug these things in. What is the cosine of 0? 1 times 3 is 3, plus 2 is 5. There's our max R value. Next one, pi over 2. What is the cosine of pi over 2? 0 times 3 is 0, plus 2 is 2. Pi. What is the cosine of pi? Negative 1 times 3 is negative 3, plus 2 is negative 1. Okay, so that has a negative R, which means when I go to pi, I'll go in the opposite direction. And then 3 pi over 2. Cosine is 0 again, plus 2 is 2. And if you want to put 2 pi in, that's great. You're going to get 5 back out. Okay, let's plot the points. 5, 0. So the R is positive. It means go in the direction of that angle. 0 is to the right, so I'm going to count out 5. There's 5, 0. 2 pi over 2. 2 is positive, so go in the direction of pi halves, which is up, okay, and count out 2 rings. When you do Limacon with a loop, the one with the negative, that's like the back end of your loop, like as far inside the Limacon as it goes. So negative 1 pi says when you go to pi, which is to the left, don't count in the direction of pi, count in the opposite direction, go backwards 1. So you're going to have 1 at what looks like 1, 0. And then 2, 3 pi over 2, go in the direction of 3 pi over 2, count out 2. Okay, and I again plotted my pole because I know I crossed through the pole, right? So the hardest part about Limacons tonight is going to be the graphing of them, because even with those points, it's like, what? Where's the Limacon? So this is where like that orientation piece can be really helpful to you. Since this was a cosine and it was plus, the majority of my Limacon is where? To the right. Okay. So like over here, this is that like really round part. It's gonna cross over a little bit to get like into my loop on the other side on the left. And then these 2 points, the pole right here, this is where my loop is. So my loop is fairly small. Okay. I actually probably do best if I start at my loop. Like I'll go in through the pole, out through the pole, think round, 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 round as best I can. Yeah, better. And pretend I went through that point. Limacon with loop. A lot of times, yours are going to look really skinny. You're going to forget about the round part because you'll do your loop and then you're just like, connect the dots, right? So yours might look a little bit skinnier. That's fine. Anybody got questions? They're kind of fun to draw once you get the hang of them. So like, bear with yourself. Give yourself some patience when you're doing your homework assignment so that you can get them done. Okay, I'm going to run through one more just really quickly so you can see a second shape. I'll post the notes, the video, and the hard copy notes if you miss anything. I'll post those online. So I'm going to run through this quick and then give you the homework assignment. If I did the ratio of A over B, that's equal to 1. So this is a limacon that is a cardioid. The max R value is 4 plus 4, which is 8. And a cardioid only has 1 0. Put in 0, pi over 2, pi, and 3 pi over 2. And plug them in. The sine of 0 is 0. This is going to give me 4. The sine of pi halves is 1. So it's going to be 4 minus 4, which is 0. There's my point at the pole. Sine of pi is negative 1. Negative 1 times negative 4 is going to be positive 4. Plus 4 will be 8. There's my max R value. And then 3 pi over 2 will be negative 1. Oh, sorry, that one's 4. Sine of pi is 0. Sine of pi is 0, so this is going to be 4. And this is the one where sine of 3 pi over 2 is negative 1. Times negative 4 is 4. Plus 4 is 8. Plot those points. 4, 0. 0 pi halves, remember that's your point where it dips and touches the pole and bounces off. Pi 4 and 8, 3 pi halves. I know some people don't like it when I go off graphs, but I'm going off the graph. Because this is a sine with a negative, the majority of my cardioid should be below the horizontal axis. So this looks something like that. Bounce off. Ta-da! Okay, the hardest part is getting the shape right, I know. It will be a little bit easier for you on your homework because you got the grids there. That will be helpful. I will post the answer key to this online tonight so that you can be checking as you go because you're going to have to be able to graph what you want tomorrow. We will still have time to go over some questions at the beginning of class. So if there's one that you cannot for the life of you figure out, you can email me, you can stop in at 8:10, or you can ask at the beginning.